Okay, so it should work like this. Okay, sorry for the inconvenience, but we changed the room from Chiara's to Ramin one. So first of all, good evening, everybody. This is the turn of Ramin. So it's the turn of the structural, seismic, and geotechnical engineering cycle. And Ramin is a 36 PhD, and he's working with Professor Felicetti, in particular in the field of structural engineering and in the field of concrete when triggered by fire. So today he will guide us through his presentation. I just remind you to know that this is the last presentation of December, and then we'll have another presentation on the 9th of January. So the next one will be in January. Okay, and yeah, so Ramin, it's your turn.
Thank you very much. Hi everyone, my name is Ramin, and today I'm really pleased to present you our last result on severe spalling in heated concrete, as you see, which is supervised by Roberto Felicetti and sponsored by a Syrian company located in France. So starting with the definition, we can say spalling or fire-induced spalling is a projection of particles, concrete particles in heated concrete with relatively high acceleration. So as you see, there are some results, there are some events in the past that you can see. For example, there are some tunnels that they were affected by these events. And then these tunnels, they couldn't work for a long time, which was had a high economical value in terms of both systematic and physical damage. The issue in this event is we do not know what are the main governing factors, actually. And that's why there is no specific criterion or any code which can give us or which can predict it well. And then in the literature, if you go in the details, you can find mainly two factors, which are firstly thermal stress, and the second one is pore pressure, addressed as the main factors in spalling. The first one is like mechanical effect of hot skin. So if you heat a material, it can expand, and then they say the thermal stress is one of the main factors. But as far as I mentioned, there is no consensus. No one knows the real behavior, and no one can predict it well. So today we want to explain it in different way. So in our new perspective, the spalling consists of two stages. The first stage is cracking, and second stage, which follows after the first one, is instability of crack. So in my thesis, I started to explain a bit about the first stage, which is the crack generation. And then, for example, I used one of the results from another PhD students to see how the combination of thermal stress and effective pore pressure can generate this spalling, which is in ultra-high performance concrete, in cylindrical one. But as you see, the combination of both of them, they give constant value for each concrete. So it is kind of material property, the threshold. But if we have different boundary conditions, the share of these two combinations is different. So by higher heating rates, we're going to have higher share of thermal stress. And then, however, mostly my thesis is concentrated in the second stage, which we think that it's more important because usually when we assessed structures after fire, we could see the crack which is there, but the instability of the crack was not completely done. So if we have a crack which is there after the spalling, in our opinion, it's even beneficial, since the crack can act as a thermal barrier to reduce the thermal or temperature inside the concrete, and then it can prevent the reballs to be exposed barely to the fire. So predicting the second stage, which is the crack instability, is more essential. So for the second stage, the main question might be, where do the fracture energy and kinetic work come from? So we should find a real source of energy which we deal with in this spalling, in this event. So as I mentioned, the whole spalling, the whole event consists of two stages. And if we want to sum up the energy that we need for the whole spalling, so we need energy which is for the fracturing of the concrete, which is about half kilojoule per square meter for 1 meter by 1 meter concrete. And then for accelerating those particles, we need about 2 kilojoule per square meter. So if we sum up both, it's 2.5 kilojoule per square meter we need for the spalling. So what are the alternatives? What are the options to provide this energy, such explosive event? So the first one is elastic strain, which is thermal stress. So for the elastic strain, the whole energy which is stored in the whole concrete cover is 1 kilojoule per square meter. So 1 kilojoule per square meter cannot provide, is not enough for that high energy. So we need to go for an alternative. And for sure, alternative in heated concrete might be the thermal energy. Imagine if just in a 1 second, 25 to 50 kilojoule is entering the whole cross section. So we have a lot of thermal energy there. And then we are comparing elephant to the mice. So this is the real issue there. But the issue is how we can convert thermal energy to mechanical work. And then the missing part can be found there in steam engine. So in steam engine, we have thermal energy, and then work can be done by means of the water. So water can be vaporized, expand, and then this conversion can be easily done. So in concrete, we have almost the same problem. So we have a porous medium, which is concrete, and these pores can be filled or semi-filled of water. And then now we have 90% of the mass, which is solid. And then these 90%, when they are heated up to 200 or 250 degrees Celsius, can provide instantly energy to the water which are stored in the small pores inside there. So in my opinion, it's even more powerful than steam engine now. So if you just want to know what are the magnitude, you can see, okay, for vaporization of just 3% of water by weight in 0.1 millimeter, very superficial layer in two sides of the crack, we need 24 kilojoule per square meter, which is equivalent to 50 degrees Celsius temperature drop, which is okay, because we have like 200 and 200 degrees Celsius there. So if you lose 50 degrees Celsius, it's fine. So we still are above boiling water temperature. And then that expansion can give us 4 kilojoule per square meter. So you can see easily how this conversion can go. So to verify all of those, to understand how much concrete is engaged in such explosive event, we started to test concrete which is heated on one side, and there's a gap on the other side. So, and then we use neutron radiography. So neutron, they show hydrogen, and the water, we have hydrogen. So we can understand how much water in each picture, in each radiography we're gonna have. Okay, so, and then when we heat from one side, the gap which is in the left side gonna be pressurized, and then we suddenly open the valve to see how much and how deep is the layer which is engaged in such event. And you see the results, just 1 millimeter depth is engaged in very small fraction of second. So 0.03 second, we are just dealing with 1 millimeter depth of concrete, which is providing vapor, vaporizing vapor, and giving vapor to the crack. In my PhD, we wanted to be more realistic. So in this time, we didn't want to have a gap which is there. We wanted to have a crack, a real crack inside concrete. So like what you see here. So a crack which is generated at the time we need that crack. So we start to think about two symmetric concrete cover, which is heated from two sides and which is separated by a crack, which will be generated at the right time. And these crack, this is the maybe interesting part, like triggered by a polymer. So this polymer has higher thermal dilation, and when you heat that polymer, it expands more from the surrounding material, which is concrete. So it pushes the concrete which is next to that, and then we have the crack there, and we'll understand if the crack gonna be unstable or not, as you see. So the idea is to fill the first half of the concrete, put the polymer there, and then fill the second half, and then as you see, we hit from two sides. All of these dimension material stuff, we optimize them by abacus, by axis symmetric models there, and you can see the first spalling that we could get. This is actually, I would say, this is the smallest material scale spalling test that you could see, let's say, in the world. And then you can see the drop of water which is coming out before the spalling. So the next step for us is to how to measure. Is there any way to measure what is happening inside that concrete? The first one was weighting the sample during the whole test. So we have a digital scale which is really precise and can give us the drying process in the whole test, and also can give us a sudden mass loss which we're gonna have inside the phenomena, as I mentioned. So the water gonna vaporize suddenly, and these can convert the thermal energy to mechanical work. And the second one is the fast monitoring of two parts of the concrete which are accelerating by means of photosensor, which are also very lightweighted and also cheap. And then since we are dealing with very huge, let's say, acceleration, thousands of G, each gram acts as 1 kilogram. So we need to be as lightweight as possible. So truss, balsa wood, photosensor, they are all designed to be as lightweight as possible. And this is the final outcome. And then this is the setup with the photosensor installed on the sample. So another designing parameter is the thickness of polymer which we put inside the concrete. It can change the timing at which the crack happening inside. So we start to have 4 different thicknesses, and then since we needed to be at the temperature about 200 degrees Celsius, we chose 0.5 millimeter one. But you see that there's a scattering. So to find out why this scattering is happening, again, we start another model. This time it's soil model, because in the soil model, we have the opportunity to impose pore pressure also, which is a leading parameter for us. So by changing a bit pore pressure, effective pore pressure inside the cracked region, you can see the scattering is happening. So for the mass loss result, I would say it is known that if we use polypropylene fiber or PP fiber, we're gonna get less spalling risk. So why this is happening? For example, you can see in some of samples, if we use PP fibers inside concrete, the concrete gonna be drier. So if we have drier concrete, we do not have water which can convert the thermal energy for us. And then another point here is if the spalling happening later, which is in higher temperature, the sudden mass loss, which is inside the spalling, is higher. And then to understand more what is the real role of moisture, we have these tests which we semi-dried 3 samples, and we test 3 moist sample and 3 semi-dried sample. You see 3 out of 3 moist sample they spalled. On the other hand, 1 out of 3 semi-dried they spalled. And then this shows that the moisture, it has the leading and crucial parameter, is the leading parameter. And then you can see that the drying rate after this spalled bond has a fast reduction, while in the other one, when it is not dry, you do not see this fast reduction. So again, we tested many concrete samples. with recycled aggregate, with cellulosic fiber, with PP fiber. And also we compared all of those with high-performance concrete, since high-performance concrete is much more sensitive than the normal one. So what is the difference between the high-performance concrete and normal concrete? As you see, after the spalling, now we have two new exposed surfaces. And then when we are dealing with normal concrete, we have a reduction in the drying rate. So the two new surfaces gonna be dry easily and fastly. So, and there is no more water there. While in sensitive to the spalling or high performance concrete, we still have high moisture which is kept there. And that's why high performance concrete, one of the reasons that high performance concrete is very sensitive to the spalling. So what we did until now, we tested all those samples in a small scale, but is it actually related to real behavior of that concrete? So what we did is we tested the same concrete in the larger scale. So large slab, 1 millimeter by 1.3 millimeter with stress, with different kind of initial stress, uniaxial stress, and then both our test setup and the larger scale test setup, they are giving this almost the same spalling risk. But the issue is when we are using a small sample, we should know how much moisture we still have in these small samples. They are not the same actually, because if we keep a small sample and large sample in the same condition, the small sample, since they have larger surfaces, they're gonna dry earlier. So we should have the same initial, let's say, moisture. And then what we got from the photosensor that I was explaining is the distance between two splinters. If we get second derivative, we will get the acceleration. And then by acceleration, we can understand what is the pressure which was generating this acceleration from inside. So this is the net pressure versus crack opening, but net pressure means how what is the pressure which induced this spalling minus the resistance of the concrete. So the resistance of the concrete is really important parameter in accelerating concrete also. So if we have sharp falling branch or mild falling branch after the peak, the difference is completely different, because the resistance of concrete can keep those two parts with each other, attached with each other. So to understand what is the real behavior of concrete after the peak, we started to think how to test those concrete. And as you see, so if we use bending, so as we go right, we have more structural effect and less material effects. We cannot get real behavior of concrete after the peak in the bending or splitting, because we have mix of both compression and tension. While in direct tensile test, it is more related to the material behavior. So we think that the direct tensile test is better to understand what is the material behavior, and then we started to model again in Abacus to understand how the boundary condition can change the behavior that we are assessing from the test. As you see, if we have two different material, a simple one, gentle and steep falling branch, if we use two different boundary conditions, what we get from the test is completely different. So it's since now we need to get the real behavior of concrete, it's better to use the fixed one. And another issue is if we go to conventional direct tensile test, there are many problems there, and we cannot use those. First of all, in the conventional direct tensile test, we have axial stability. So we have two columns. This is maybe the instrument that many people they know. This instrument is 100,000 euros. It's not cheap. So as you see, when you start pulling your concrete, those columns are compressed and the beam is in flexure. So there is the big elastic energy stored in whole system. It's kind of network of springs, that you are pulling one side, so they are all working, they are storing energy, and when the crack is starting, there is like a failure in one of those springs. So all the accumulated energy, elastic energy, gonna be released there in a defect. So that's why we don't need this, because we need to come back with the activator to compensate this stored energy. And then this is maybe feasible for the normal concrete, but for high-performance concrete, which we have very steep falling branch, we cannot control this, the test. And then the other issue is rotational stability in conventional direct tensile test. So usually, as you know, concrete is not homogeneous. Mostly we have a weaker side and a stronger side. When we are pulling, one of the side, which is weaker, it's gonna reach to the peak, and the crack start from one side. And then after that, you are cracking on one side and you're unloading on the other side. So you're gonna get a mixed behavior of cracking, unloading, without getting the real behavior. Another issue, which is mostly related to when we are using fixed boundary condition, is when it's not just the direct tensile test there, so we will get also shear. So it's shear plus tensile, and then we will get incline onset or bifurcation, which is mostly you can see in literature review. We were thinking that we should design a new test setup, and in this new test setup, instead of having one actuator, we need 3 actuators, which can pull concrete from 3 different sides. So if the crack is starting in one side, we can easily understand and compensate it to have a planar crack all around the sample. And then actuators are pushing 2 platons to reduce the elastic energy stored in the system. And then we did decide a lot of different stuff to reduce the elastic energy again, which is stored there. Like we didn't use compressed oil, we used upper bone screw nuts, stiff machine table, all of those to reduce the elastic strain. And this is the outcome. So with the low inertia brushless motor, which they have really high acceleration, precise gearbox, and with all of those, we came up with traction, which we called it. And this is now available in our lab. And this is the first result. So for the high performance concrete, as you see, we could get good repeatability, even if the concrete is very brittle. Like in the normal concrete, it's really easy to get it. But when we are dealing with high performance concrete, this falling branch is really steep. And in the normal condition, you cannot get it. So as you see, we could get all of those falling branches. And another advantage of this new test setup is when we are done with our sample, when we pull the samples, we're gonna have 2 samples for splitting. So we can also test them in a splitting test to compare all of those with each other. So another thing that I wanted to mention today is, as I mentioned, high performance concrete, they are really sensitive to the spalling, why the normal concrete is not. Another reason that I can mention is here. So you see in high performance concrete, after 0.01 millimeter, we lose 50% of resistance of the concrete. So the concrete will lose mostly all of its strength when it is cracking. But when we are using normal concrete, it's not the case. So we still have resistance of concrete which is working. So the concrete is still can resist direct tensile, which is another advantage of normal concrete in spalling, I would say. And maybe I can stop here. Thank you for attention. It's just QR code for my research.